Welcome to this problem walkthrough. In this video, we'll be exploring LeetCode problem number 1662, check if two string arrays are equivalent. This problem challenges us to verify if two string arrays represent the same string when concatenated. We'll analyze the problem, consider different approaches, and break it down step by step. Let's get started. The problem asks us to determine if two string arrays, word1 and word2, represent the same string when their elements are concatenated in order. For example, if you concatenate all the strings in word1 sequentially, and do the same for word2, the task is to check if those two resulting strings are identical. If they are, we return true, otherwise, we return false. The input consists of two lists of strings, where each string is made up of lowercase English letters. The size of each list and of the strings is constrained to ensure that the total number of characters in each list does not exceed 1000. The output is a Boolean value that indicates whether the concatenated strings are equal or not. To better understand the problem, let's look at an example. If word1 is ABC and word2 is BC, we first concatenate the elements of word1 to form the string of plus C, which is ABC. Similarly, concatenating the elements of word2 gives a plus BC, which is also ABC. Since the concatenated results are the same, the output in this case is true. Another example is where word1 is CB and word2 is BC. Here, concatenating word1 produces a plus CB, which is ACB, while concatenating word2 produces a plus C, which is ABC. Since these two strings are different, the output is false. Now consider another example where word1 is ABCDEF and word2 is ABCDEF. Concatenating the elements in word1 gives ABC plus D plus F, resulting in the string ABCDFG. For word2, concatenating its elements gives ABCD plus F, which is also ABCDFG. Since both concatenated strings are equal, the output is true. This demonstrates how the solution relies on comparing the full concatenated strings of word1 and word2 to determine equivalence. The problem also comes with constraints and edge cases to consider. The constraints ensure that the input size is manageable, with each list containing up to 1000 strings, and the total number of characters across all strings in each list not exceeding 1000. Edge cases include scenarios like the smallest possible input, where both arrays contain a single one-character string, or cases where the total concatenated lengths of word1 and word2 differ. Although empty strings are not allowed by the constraints, it's good practice to ensure your implementation can handle them gracefully. Additionally, testing with the maximum constraints helps verify that your solution is efficient and robust even for large input sizes. To solve this problem, we want to determine if two string arrays, word1 and word2, represent the same string when all their elements are concatenated. Let's start by discussing the brute force approach. The intuition here is straightforward. We concatenate all the elements of word1 into a single string, do the same for word2, and then directly compare the two resulting strings for equality. The process is simple. Use a loop to combine the strings from each array, store the concatenated results as string 1 and string 2, and check if they are identical. The time complexity of this approach is O, n plus m, where n and m are the total lengths of the strings in word1 and word2, respectively. However, it also requires O, n plus m, space to store the concatenated strings, which can be a drawback for large inputs. This makes it a good starting point but not the most efficient solution. Although the brute force approach is easy to implement, it has a key limitation: the additional space required for the concatenated strings. To address this, we can use a more optimized approach with two pointers. Instead of explicitly concatenating the strings, we simulate the process by iterating through word1 and word2 character by character, comparing their contents directly. The key idea is to use two pointers, one for each array, and track not only the current string in the array but also the position within that string. If at any point the characters differ, we can immediately return false. On the other hand, if we traverse both arrays completely and the characters match at every step, we return true. This approach avoids the need for extra memory, making it more efficient while still maintaining a clear structure. By moving the pointers to the next string in an array when needed, we ensure that the process is seamless and aligns directly with the problem requirements. When analyzing the complexity of the two-pointer approach, we find that it runs in O, n plus m, time, as we are still iterating through all the characters in word1 and word2. However, the space complexity is a major improvement. It is just O1, as no additional memory is allocated for storing concatenated strings. This makes it highly efficient for larger inputs. While the implementation is slightly more complex than the brute force method, the trade-off is worthwhile for the performance gains. Alternatively, we could consider using Python's itertools.chain to solve the problem. This method creates lazy iterators over the characters of word 1 and word 2, allowing us to compare their contents directly using the all function. The time complexity remains O, n plus m, and the space complexity is also O1, since itertools.chain does not generate intermediate strings. This approach is concise and leverages Python's built-in libraries, but it may feel less intuitive for beginners compared to the two-pointer strategy. Among the approaches discussed, the two-pointer iteration method stands out as the best choice. It combines efficiency in both time and space with a clear, logical implementation. Although the brute force method is simpler, it incurs significant memory overhead due to the concatenated strings, limiting its scalability. On the other hand, the itertools.chain approach is elegant and concise but requires a good understanding of Python's libraries, which might make it less accessible for some users. The two-pointer strategy strikes the right balance between performance and simplicity, making it an ideal solution for this problem. It avoids unnecessary memory usage while maintaining clarity, ensuring that the solution is both robust and practical for a wide range of input sizes. To solve this problem, we need to determine if two string arrays, word 1 and word 2, represent the same string when all their elements are concatenated in order. Each array can contain multiple strings, and our task is to concatenate these strings sequentially and check if the resulting strings are identical. For example, if word 1 is ABCD and word 2 is JBCD, concatenating their elements results in the strings ABCD and ABCD, which are equal. One straightforward way to solve this is to concatenate all strings in each array into two separate strings using Python's join method. Once we have the concatenated strings, we simply compare them using the equality operator. If they are the same, we return true, otherwise, we return false. This approach is simple but has some limitations, as we'll see shortly. Another method to solve this problem is by using a two-pointer approach that avoids full concatenation. This method is more efficient in terms of space. Here, we maintain two pointers, I and j, to traverse word 1 and word 2, respectively. Additionally, we use two inner indices, inner_i and inner_j, to track our position within the current strings of each array. We compare characters at the current positions of word 1 and word 2. If at any point the characters differ, we return false. Otherwise, we advance the inner indices to the next character. If we reach the end of a string in one array, we move to the next string in that array. The process continues until both arrays are fully traversed. If all characters match and both arrays are exhausted, we return true. This approach ensures we only compare the characters necessary without creating additional concatenated strings. When comparing the two approaches, it's important to consider their trade-offs. The concatenate and compare method is simpler to implement, but it's not efficient for large inputs because it requires extra space for the concatenated strings, resulting in L1 plus L2, time and space complexity, where L1 and L2 are the total lengths of word 1 and word 2. On the other hand, the two-pointer approach eliminates the need for extra space, making it L1 plus L2 in time but O1 in space. Additionally, we must consider edge cases. For instance, if both arrays are empty, we should return true since they represent the same empty string. If the total lengths of the two arrays differ, the two-pointer method can detect this mismatch early and avoid unnecessary comparisons. Lastly, single-element arrays such as ABC versus ABCD must be handled correctly to ensure accurate results. These nuances highlight the robustness of the two-pointer approach in handling various scenarios. In terms of complexity analysis, both approaches have a time complexity of L1 plus L2, where L1 and L2 are the total lengths of word 1 and word 2. This is because every character in both arrays is processed exactly once. However, the space complexity differs significantly between the two methods. The concatenate and compare approach requires L1 plus L2 space for the concatenated strings, while the two-pointer approach only uses a constant amount of space, O1, as it relies on pointers and indices without creating additional data structures. This makes the two-pointer approach particularly suitable for scenarios where space efficiency is critical. By understanding these trade-offs, you can choose the best approach for your specific use case. This solution implements the check if two string arrays are equivalent problem in Python. First, given two string arrays word1 and word2, the goal is to determine if their concatenated forms are equivalent. The function ArrayStringsAreEqual achieves this by using Python's join method, which efficiently concatenates all strings in a list into a single string. The strings from word1 are joined into concatenated 1, and similarly, the strings from word2 are joined into concatenated 2. Finally, the function compares the two concatenated strings using the equality operator == and returns true if they are identical, otherwise false. This approach ensures clarity and optimal performance, as joining strings is linear in time complexity, O(n), where n is the total number of characters across all strings in the arrays. The code handles edge cases, such as empty arrays or arrays with empty strings, gracefully because the join method works even when there are no characters to concatenate. Overall, this is a clean and efficient solution for the problem. This is the Java implementation for LeetCode problem number 1662, check if two string arrays are equivalent. The logic mirrors the given Python implementation. The ArrayStringsAreEqual method concatenates the strings from both input arrays using a string builder for efficiency, and then compares the resulting strings using the .equals method. Key differences in Java include explicit type declarations and using string builder instead of Python's join method for concatenation. To solve this problem, we need to determine if two string arrays are equivalent. This means that when we concatenate all the strings in the first array, the result should match exactly with the concatenated result of all strings in the second array. Let's take the first example to understand this better. Here, word1 is given as C, and word2 as ABC. First, we concatenate all the strings in word1 using Python's join function. This combines ab and C to form the string ABC. Similarly, for word2, we concatenate A and BC, which also results in the string ABC. Now that we have the concatenated results from word1 and word2, we compare them. In this case, since ABC is equal to ABC, the result is true. The second example highlights a case where the strings do not match. Here, word1 is ACB, and word2 is ABC. When we concatenate the strings in word1, we get A combined with CB, resulting in ACB. For word2, we concatenate AB and C, giving us ABC. Now, comparing these two concatenated results, we see that ACB is not equal to ABC. Therefore, the output for this example is false. This demonstrates how the solution correctly identifies mismatches between the concatenated results. The third example introduces a scenario with empty strings. When both word1 and word2 contain only an empty string, as in, the concatenated result for both is simply an empty string. Here, combining the single element in word1 results in an empty string, and the same happens for word2. Comparing these two empty strings, we find that they are equal. Thus, the output for this case is true. This example shows that the solution handles edge cases like empty inputs correctly. Finally, let's break down why the solution works so efficiently. By using the join function, we can concatenate all elements of word1 and word2 into single strings quickly and cleanly. This is crucial because the problem boils down to comparing these final concatenated strings. Python allows us to compare strings directly with the == operator, which is both simple and effective. Additionally, the solution accounts for various edge cases, such as when the arrays contain empty strings or have different numbers of substrings. The overall time complexity is O(n plus m), where n and m are the lengths of the concatenated strings from word1 and word2, respectively. This ensures the solution is both optimal and straightforward, leveraging Python's built-in string operations to solve the problem seamlessly. To analyze the time complexity of the given solution, we need to break down the major operations step by step. First, consider the concatenation of all strings in word1. The operation .join, word1, iterates through each string in the array and combines them into a single string. The time taken for this operation depends on the total number of characters in word1, which we denote as n. Therefore, this step takes O(n) time. Similarly, for word2, the concatenation process works in the same manner. If the total number of characters in word 2 is m, the operation .join word 2 will take m time. These two operations are the main contributors to the time complexity so far. Next, we have the comparison of the two concatenated strings using the equals operator. This comparison checks the two strings character by character. In the worst-case scenario, if the strings are identical and of equal length, the comparison would take min n m time. However, since the concatenation operations dominate the overall runtime, the time spent on comparison is generally negligible in comparison. Combining these steps, the overall time complexity is determined by the concatenation of both word 1 and word 2, which results in n plus m. This linear complexity is efficient given the nature of the problem. Now turning to space complexity, let's analyze the memory usage step by step. First, consider the space required for the concatenated strings. When we execute .join word 1, a new string is created to store all in characters of word 1. This operation requires n additional space. Similarly, for word 2, the .join word 2 operation creates a new string that holds all m characters, requiring m space. Apart from this, the function uses a few temporary variables such as concatenated 1, concatenated 2, and the result of the comparison. These variables occupy constant space, or O1, regardless of the input size. As a result, the overall space complexity is dominated by the storage of the concatenated strings, making it n plus m. When comparing this approach to a brute force method, a naive solution would involve manually iterating through word 1 and word 2 character by character to compare corresponding characters. This avoids the need to concatenate the arrays, reducing space complexity to O1. However, it adds implementation complexity and requires careful management of indices. While the brute force approach still has a time complexity of n plus m, the current solution is more intuitive and leverages efficient built-in operations like join and equals. This simplifies both implementation and debugging. Considering best, average, and worst cases, the time complexity remains n plus m for non-empty inputs, as concatenation and string comparison scale linearly with the input size. In the best case, where both arrays are empty, the time complexity drops to 1, since no operations are performed. This makes the current approach both efficient and practical for solving the problem. In this problem, there are several common mistakes to watch out for, and understanding them can help you avoid unnecessary errors. First, one of the most frequent issues is concatenating strings without verifying their order. Keep in mind that string comparison is highly order sensitive. For example, while ABC and BC are equivalent, ABC and ACB are not, because the sequence matters when concatenating. Another mistake is overlooking empty strings in the arrays. For instance, should be treated as but forgetting to handle these cases explicitly can cause bugs. Lastly, using the join method inside a loop is a common inefficiency. Since string concatenation is an n squared operation in languages like Python due to string immutability, repeatedly appending strings can make your solution unnecessarily slow. Instead, always use .join on the entire array to achieve linear time complexity. These are some pitfalls to be mindful of as you approach this problem. Another area where mistakes often arise is assuming that word 1 and word 2 will always have the same number of elements. This assumption can lead to incorrect results, as the two arrays may differ in length but still be equivalent once concatenated. For example, ABC and BC should compare as equal, even though their lengths differ. To handle this, it's important to validate the concatenated strings as full entities rather than relying on array lengths. Additionally, edge cases with special characters can complicate the problem. For example, AB and B are equivalent, but and AB are not. These differences highlight why you cannot make assumptions about the content of the strings. Always treat the strings exactly as they are given, ensuring you handle spaces, symbols, and other special characters properly. When working on this problem, there are several key insights that can help you impress an interviewer. First, recognize the importance of efficient string manipulation. For example, using .join instead of repeated concatenation not only avoids inefficiencies but also demonstrates your ability to optimize operations. Additionally, you should be prepared to analyze a variety of edge cases, including empty strings, arrays of unequal lengths, and strings with special characters. Highlighting these cases during your explanation shows that you're thorough in your approach. Time complexity is another critical area to discuss. Explain the difference between O(n)² solutions, such as repeated concatenation inside a loop, and O(n) solutions, like joining an entire array at once. This indicates that you think about scalability. Lastly, try to generalize the problem. For instance, consider scenarios where the arrays are extremely large or where the task involves comparing substrings instead of full concatenation. This kind of forward thinking can set you apart in an interview setting. This problem also has connections to other LeetCode problems, which can deepen your understanding of string-related concepts. For example, LeetCode number 28, find the index of the first occurrence in a string, focuses on substring search and reinforces efficient string operations. LeetCode number 125, valid palindrome, deals with handling edge cases for spaces and special characters, which is highly relevant here. Similarly, LeetCode number 344, reverse string, is a simpler problem that strengthens your grasp of string and array manipulations. Finally, LeetCode number 3, longest substring without repeating characters, introduces sliding window techniques, which are useful for optimizing string traversal. Studying these related problems can enhance your ability to recognize patterns and apply techniques across different challenges. There are also alternative approaches to solving this problem, each with its own trade-offs. One option is the two-pointer approach, where you traverse both arrays simultaneously, comparing characters one by one without fully concatenating the strings. This method is memory efficient and avoids creating large intermediate strings, but it requires careful implementation. Another approach is direct string concatenation, where you combine word 1 and word 2 into two complete strings and compare them. This is simple and intuitive but can be memory intensive when the arrays are very large. A third option is character-by-character comparison using iterators, which allows you to traverse the arrays efficiently without full concatenation. However, this method requires meticulous handling of iterator logic and edge cases. Each of these approaches has its strengths and weaknesses, so choosing the right one depends on the constraints and requirements of the problem. Great job working through this problem with me. Today, we focused on comparing string arrays efficiently and highlighted key concepts like string manipulation and algorithmic complexity. I hope you found this walkthrough helpful. Don't forget to practice similar problems and refine your skills. Thank you for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!